Our first talk will be by Quentin from Toulouse.
Okay. Okay, so hello everyone, I'm Quentin Pilate. I'm a third-year PhD student working at IRAP in France. And as a small spoiler, as you can see here, I'm going to present you the first images of the photosphere of Antares using spectropolarimetric. So red supergiants are very massive and cool evolved stars. And in 2022, we observed the red supergiant Antares with espadon, and we found a strong linear polarization signal at its surface. As you can see here, Stokes Q is represented in blue, Stokes U in red, and the total linear polarization in green. The first question that we can ask is, where does this linear polarization come from? The answer is not from the Zeeman effect, but this linear polarization signal is due to brightness inhomogeneities which are caused by the large convective cells present at the surface of red supergiant. Knowing that this signal is due to brightness inhomogeneities, it opens the path to produce spectropolarimetric images of the star. But first of all, in a nutshell, how can we produce images of the star using spectropolarimetry? First of all, I would need the velocity of the star, which is represented as the dotted line. And I'm going to assume that the signal that we receive on Earth is due to rising plasma only. So the signal is blue shifted compared to the velocity of the star. The more blue shifted the signal is, the closer it is coming from the center of the stellar disk. Vice versa, the closer the signal is from the velocity of the star, the closer it is coming from the stellar limb. I would also need an angle that I can compute through polar angle theta, which is just the ratio of Stokes U over Stokes Q. And finally, I'm going to assume that the brightness is proportional to the total linear polarization Q squared plus Q squared. Knowing that, I can produce images of the photosphere of Antares. So north is up, east is left, and on the left you recognize the profile that I showed you before. But in fact, this profile, the dots are the observation, and the lines are the reconstructed Stokes profile from this image. So you see that it fits perfectly the data, which is quite impressive. And overall, more than that, we have monitored Antares during 1.5 years to probe both short and long-term dynamics of the photosphere. There are basically between 1 and 3 convective cells at the surface of the red supergiant. As you can see here in July 22, there is only 1 cell, but in July 2023, there are 3 cells. Overall, there are different time scales associated to convection, and the largest convective cells can live up to a whole year. As you can see in July 2022, there's a hot spot here, which is staying at the surface up to July 2023. Not represented here, but we have measured a magnetic field through Stokes V, so the circular polarization, and it's basically between 1 and 2 Gauss, which is basically what we find in other red supergiants like Betelgeuse. So overall, the takeaway message is that for red supergiants, we don't need interferometry to produce images of the photosphere of the star. We just need linear polarization. And I would conclude with future work that we will study how stellar winds are triggered in Antares and compare to the one we have found in Betelgeuse. Thank you for attention.
Thank you. Yes, question, go ahead.
Thank you very much for a very interesting presentation. You measured Stokes U and Q profiles.
Yeah.
A deeper profile, or you just used some particular line?
As you can see, the velocity, so yeah, it is.
What is the limit errors?
This one.
There are many different solutions that we can find, in fact. So I don't have time, but of course, with linear polarization, we suffer from 180-degree ambiguity. So we can rotate those brightness, those images, and the observed image will still fit the observed Stokes profile. So of course, we need interferometry to disentangle where the bright spot is. Is it located, for example, northeast and the southwest?
Thank you so much.